In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. So let's see the questions. The voltage gain of the common emitter amplifier is option A, directly proportional to collector bias current, inversely proportional to collector bias current, independent of collector bias current, proportional to square of collector bias current. So he's asking the voltage gain of CA amplifier. Basically the voltage gain is nothing but output voltage divided by input voltage. Okay, he's asking for the collector bias current. Now if you see, this is a circuit, this is R1, R2, this is a transistor with collector resistance, RC, RE, emitter resistance, VCC. So the output voltage is collected across the collector. The output voltage is nothing but the collector current multiplied by the load resistance, that is RC, divided by input voltage. Input voltage is the base current multiplied by input resistance. The base current multiplied by input resistance. So if you observe this formula, the voltage gain is directly proportional to the collector current. Let it be the collector bias current, or you can call it as a collector AC current, whatever it is. But the voltage gain is directly proportional to the collector bias current. So answer is option A. We'll see the next question. As compared to BJT amplifier, an amplifier made using JFET is likely to have JFET, junction field effect transistor. It has got specific features. One of the features is high input impedance. High input impedance. It has got very high input resistance, because of which the noise will reduce a lot. It has got a low noise capacities, and it is a voltage controlled device. BJT is a current controlled device. JFET is a voltage controlled device. These are the specific advantages that we have. By nature, this is a transconductance amplifier. It is a transconductance amplifier. Whereas BJT is a current amplifier. Input is current, output is also current for BJT. For JFET, input is voltage, output is current. So output current by input voltage is nothing but transconductance. Okay, these are the specific features of junction field effect transistors, because of which it finds very wide applications in the high frequency applications, high frequency devices. So the answer is option D. It has got a very high input resistance. Let's see one more question. The gain of the single stage BJT amplifier in emitter follower configuration when RC is equals to 22, RE is equals to 2.2. So here a small correction is there. I don't think this question is asked for emitter follower. It is asked for CE configuration, common emitter configuration. Whereas for emitter follower, the configuration is common collector. Okay, I think there is a correction in this question, because if you observe for the emitter follower, the common collector configuration itself is the emitter follower. This is the emitter follower. If you see the circuit diagram here, input is base, output is at the collector, at the emitter. This is the emitter resistance. Output is taken here itself, and the collector resistance will be here. This is VCC. Okay, so if you see the voltage gain here, the voltage gain is nothing but output voltage by input voltage. Input voltage is given at the base, so output voltage is taken across the emitter resistor. So output voltage is nothing but IE, emitter current, multiplied by RE, emitter resistance, divided by input voltage, that is VB. So if you see this, IE and RE divided by input voltage VB is nothing but again the voltage across the emitter only. See, whatever the input voltage is applied at the base will drop at the resistance RE only. Here the junction voltage, the voltage drop across the base emitter junction is only 0.7 volts. So if you remove that 0.7 volts, the remaining voltage will be dropped across this emitter resistance only. So Even if you apply the KVL at the input loop, the input voltage will be approximately equal to IE again, plus some IE and RE dash will come. This is the emitter model resistance. This is very, very small. This RE dash component is very, very small. So that can be neglected. So approximately this becomes 1. It is closer to unity. This is for common collector or emitter follower configuration. But here he has given the collector resistance and emitter resistance both and asking to calculate the gain. So this must be for common emitter configuration. For common emitter configuration, input is at the base, output is at the collector. This is the collector resistance, output is collected here. And this is the emitter resistance. So the voltage gain AV will be output voltage divided by input voltage. Output voltage is collector current multiplied by collector resistance divided by input voltage is nothing but emitter current multiplied by RE dash, small emitter model resistance plus RE. If you apply KVL here, there is a small emitter model resistor inside the emitter junction, that is RE dash, which is very, very small value, and RE. The input voltage will drop across this. So the collector current and emitter current both will be approximately same. So here the voltage gain AV is equals to RC divided by RE dash plus capital RE. RE dash can be neglected because it is very small value, and given voltage gain will become RC divided by RE. So if you substitute the values 22 kilo ohm divided by 2.2 kilo ohm, the voltage gain value will be 10. So answer is option B. So I feel there is a small correction in the question. This is not emitter follower but common emitter configuration. If it is really emitter follower, the voltage gain must be closer to 1. But we don't have any such options which are nearly 1. Next question. The voltage gain of the BJT amplifier is, the voltage gain of the BJT amplifier is nothing but output voltage divided by input voltage. Output voltage can be written as collector current multiplied by collector resistance. Input voltage is base resistance multiplied by base current. So this collector current and base divided by base current, you can write it as current gain multiplied by RC divided by RB or RN. The same thing you can write as the current gain. The collector resistance can be written as load resistance. Input resistance, the base resistance can be written as input resistance. So answer is option C, current gain multiplied by RL divided by RI. We'll see the next question. The configuration of the transistor in the circuit is, when we are asked such kind of questions, we have to check thoroughly. If you want to find out the configuration, first where is the input? Find out the input terminal. Next, what is the output terminal? If input terminal and output terminals are found, the remaining terminal is the common terminal. Remaining terminal, whatever terminal is there, that is remaining terminal is common terminal. Okay, now let's see. See, this is the transistor. I am giving input at a base. This is the base. I am giving input here, taking output at the emitter. Now you tell me, input is at the base, output is at the emitter. What is common now? The remaining terminal is collector. So this is called a common collector configuration. Common collector configuration. Similarly, I will draw one more circuit. This is the transistor. Input is given at the base, output is taken across the collector. Output is taken across the collector. Okay, now you tell me what kind of configuration is this? This is a input is at the base, output is at the collector. So this is a common emitter configuration because the remaining terminal is emitter only. Similarly, I'll draw one more circuit. Input is at the emitter. This is the emitter. I am giving input here, taking output at the collector. Now you tell me what is this? Input is at the emitter, output is the collector. So the remaining terminal is base. So this is common base configuration. In this way you have to find out. Now you look at the circuit. Input is given at the base. Input is given at the base. Output is taken at the emitter. This is the emitter. Output is taken across the emitter. So the remaining terminal is a collector, that is common. So this is called a CC configuration, common collector. Input is at the base, output is at the emitter. So it is a common collector configuration. We'll see the next question. The self bias provides stable Q point. Answer is option A. Self bias is majorly used to offer the stable Q point. How does it provide the stable Q point? We'll see the circuit first. This is the circuit diagram. Resistance R1, R2, transistor with collector resistance and emitter resistance. This is the basic circuit. Input is given at the base, output is taken across the collector. There is some VCC supply. The equivalent circuit diagram can be given like this. This is V Thevenin's. V Thevenin's is nothing but the voltage across R2. This is also called as VB. And there is R Thevenin's. R Thevenin's is nothing but R1 parallel with R2. R Thevenin's is nothing but R1 parallel with R2. This is the transistor, emitter resistance R. This is the equivalent circuit of the original diagram. This is collector resistance and this is output. Okay. Now for this circuit, the stability factor, if you see, the stability factor S is equals to 1 plus beta divided by 1 minus beta DIB by DIC, the change of base current with respect to collector current. This is a stability factor formula. For self-bias circuit, for self-bias, DIB by DIC is given as minus RE, emitter resistance, divided by Thevenin's resistance plus RE. This is the value. So if you substitute this value in the S stability factor formula, we will get 1 plus beta divided by 1 plus beta RE divided by R Thevenin's plus RE. So if we choose appropriate values of RE and R Thevenin's such that RE is greater than R Thevenin's, that is the R1 and R2 values are selected in such a way that the parallel combination of R1 and R2, that is R Thevenin's, is much lesser than emitter resistance. Then what happens? The stability factor S becomes 1 plus beta divided by 1 plus beta, that is approximately closer to 1. So this is what we exactly need. When the stability factor is closer to 1, that makes the transistor configuration, that makes the transistor, the entire circuit, independent of beta values, VB values and temperature, independent of temperature, changes in base emitter voltage, changes in beta value. So that at that point we can tell that the circuit is very stable. The Q point is stable. So answer is option A. Like the video, share the video and subscribe to the channel for better content and more videos. We'll see the next question. In the figure, what is the base current if VBE, the base emitter voltage, is 0.7 volts? So he's asking for the base current. So if you apply the Kirchhoff voltage law in the input loop, you will get the answer. By applying KVL, Kirchhoff voltage law, in input loop, we'll get VBB is equals to IBRB plus VBE. So VBB is 10 volts. The base current is not known. Base resistance is 1 mega ohms plus the base emitter voltage is given as 0.7. So from this we can calculate the base current is 9.3 divided by 10 to the power of minus 6. So it is nothing but 9.3 micro amperes. So answer is option D. We'll see the next question. The value of RB, that is the base resistance required to drive the transistor circuit into saturation. So he's telling the transistor need to be driven into saturation mode, and what is the value of base resistance required for that. Okay, now we'll calculate the saturation currents first. We'll apply the Kirchhoff voltage law in the output loop. So by applying KVL in the output loop, we will get VCC is equals to RC into IC plus VCE, collector to emitter voltage. VCC is 10 volts, RC is 1 kilo ohm, that is 1 into 10 to the power of 3. The collector current is nothing but IC sat. We are calculating the collector saturation current. Plus VCE becomes VCE saturation. So what is the VCE saturation? It is a 0.2 volts, which is standard value. So from this, you can tell that the IC saturation is 9.8 milliamps. Then from this, we can easily calculate IB saturation. Why we are calculating the saturation values? Because he's telling the transistor should be driven into saturation. So if the transistor is working in saturation, the current flowing through the collector resistance is the saturation collector current. That's why. Similarly, the base current that is flowing into the base terminal is the base saturation current, IB saturation. So what is IB saturation? That is nothing but IC saturation divided by beta. That is 9.8 milliamps divided by beta value is 20. So the IB saturation will be approximately it will be closer to 500 microamperes. Now you can calculate the base current. Base current can be calculated by applying the Kirchhoff voltage law in the input loop. By applying KVL at the input loop, you will get the input voltage is equals to IB saturation into RB resistance plus VBE. So the VB is usually 0.7 volts. The input voltage is 10 volts. IB saturation is 500 microamperes. Base resistance RB plus base emitter voltage will be 0.7 volts generally. So from this, you can tell the base resistance will be approximately closer to 20 kilo ohms. So answer is option C. In the circuit shown, VI, that is the input voltage, is 2.7 volts, VBE is 0.7 volts, and beta is far greater than 1. So GM, that is nothing but transconductance of the transistor is. GM is nothing but transconductance of the transistor. So the transconductance formula is the output current IC divided by input voltage, that is the thermal equivalent voltage VT. VT is usually a fixed value. VT is usually 25 millivolts, that is a fixed value. So we need to find out the collector current or emitter current, because collector and emitter current both will be approximately same. So by applying the Kirchhoff voltage law in the input loop, you will get V1 is equals to VB, base emitter junction voltage, plus emit voltage across the emitter resistance. So V1 is 2.7 volts. The base emitter voltage is given as 0.7 volts. Emitter resistance voltage is nothing but emitter resistance 200 ohms multiplied by emitter current. So the emitter current is equals to approximately 2 divided by 200, which will be equal to 0.01 amps, that is nothing but 10 milliamps. So this is the emitter current. Here it is considered that emitter current and collector current are approximately same. So now the transconductance GM is equals to collector current IC divided by VT. So GM is equals to 10 milliamps divided by 25 millivolts. So the transconductance GM is equals to 400 millimos. This is nothing but millimos. 400 millimos. So answer is option B. For those who want the derivation of this transconductance formula, I'll just explain the derivation, how it gets derived. Okay. If you see the derivation here, This is the transistor, and this is the collector current that is flowing IC. This is the base current IB, and this is the base emitter junction voltage VBE. Okay. Now the transconductance is basically conductance means the change of current divided by voltage. Transconductance means the change in collector current IC divided by the change in input base emitter junction voltage. This is the basic formula that we have. So here the collector current can be written as with the diode current equation. This is 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 the reverse current, e to the power of VD. VD is not VD divided by eta VT. This is the current equation, diode current equation. Similarly, we are writing collector current as IS e to the power of, here in place of VD we will get VBE, base emitter junction voltage, divided by eta is generally considered as one value here, so VT. Now this is the equation 1 we got by differentiating equation 1 with VBE, that is base emitter junction voltage. So we'll get the transconductance GM is equals to dou IC divided by dou VBE. So if you differentiate this equation with VBE, you will get IS is the constant exponential e to the power of VBE by VT multiplied by 1 by VT. So this entire term IS e to the power of VBE VT becomes IC. So it will be equal to IC divided by VT. So the transconductance GM is equals to IC divided by VT. This is the derivation. With this, we are using this formula. We'll see the next question. If the emitter follower has VCQ, this is Q point as 6 volts and ICQ is 200 millivolts, emitter resistance is 10 ohms. The maximum peak to peak unclipped output is. So if you see the output characteristics, it will be like this. These are the output characteristics, IE and VC. The load line will be selected in this way. The Q point is basically selected in the middle of the load line. So he's telling this particular Q point is nothing but this particular Q point here. It is nothing but this is 6 volts and this is 200 milliamps ICQ, the collector current. Now the maximum peak to peak unclipped output is. So you can calculate from this. This is a midpoint. The emitter voltage will be. The emitter voltage is nothing but the emitter current multiplied by emitter resistance. Here I am considering emitter current is equals to collector current. So ICRE, that is 200 milliamperes multiplied by 10. So that is equals to 2 volts. But this is only one side. He is asking peak to peak voltage. So the positive peak will be 2 volts. Negative peak is also 2 volts. So peak to peak voltage value will be equal to 2 times of ICRE. So that is equals to 4 volts. So the peak to peak value will be always 2 times of the Q point values. That is 4 volts. Answer is option B. Hope you understood this problem. Means the 2 volts. Now it is 6 volts. Na? VCQ is 6 volts. So here 2 volts will be there variation. And the positive peak is also 2 volts variation will be there. So peak to peak value will be 4 volts. The positive peak is 2 volts and negative peak is also 2 volts. We'll see the next question. Like the video, share the video and subscribe to the channel for better content and more videos. A BJT has alpha is equals to 0.99. The base current IB is equals to 25 microamperes and IC B naught is 200 nanoamperes. The collector current is. The collector current is basically given as beta IB plus 1 plus beta IC B naught. Okay. Now the collector current IC is equals to beta value is given Sorry, alpha value is given, beta is not given. So you can calculate beta from alpha value, that is beta is equals to 1 alpha divided by 1 minus alpha. So 0.99 divided by 1 minus 0.99 is equals to 99. Substitute the value here, 99. The base current is 25 microamperes plus 1 plus beta is 100. ICB naught is 200 nanoamperes. So the collector current IC will be equal to approximately equal to closer to 2.5 milliamps. So answer is option A. Next question. An NPR bipolar transistor with a current gain of 100 is biased in a saturation mode. This is very important. Saturation mode, it is biased. If the base current is increased by delta B, then what happens to collector current? So when transistor is in a saturation mode, the condition is the collector current flowing should be greater than or equal to IC saturation current. The present collector current that is flowing in the transistor, that is here, this is the transistor, this is RC, and there will be some base current that is flowing, there will be collector current. The present base current or the collector current that is flowing must be greater than or equal to IC saturation. Okay, that is the condition. Or the present base current that is flowing must be greater than or equal to IB saturation. This is the condition for the transistor to enter saturation region. Now let's consider the first equation. IC must be greater than or equal to IC saturation. This IC can be written as beta into IB greater than or equal to IC saturation. Okay. Now he is asking delta B. The base current is changed by delta B. So if you take from this equation, the change in delta B must be greater than or equal to the change in the collector current. The change in the IC saturation. So the answer is IC saturation. So if you substitute the value of beta here, the change in the collector current saturation less than or equal to beta value is 100, change in IB. So now with this the answer is option C. We'll see the next question. For the circuit shown in figure, the transistor parameters are VBE, base emitter voltage is 0.7, beta is 99, beta value is 99, base emitter voltage is 0.7, VC value at this point, collector point, VC is set to 7.5 volts. So this entire thing is 7.5 volts, he is telling. VC point is 7.5 volts. The required value in kilo ohms of RB is, what is the value of RB? So first, we will calculate the collector current, which is equals to VCC minus the collector current is here in this portion. VCC minus VC divided by collector resistance. So 10 minus 7.5 divided by 1 kilo ohm. So collector current is equals to 2.5 milliamps. So now the base current will be, the base current is nothing but the collector current divided by beta. That is 2.5 milliamps divided by 99, which will be equal to approximately 25 microamperes. So now the emitter current is nothing but the sum of base and collector currents will be equal to 2.525 milliamps. So now if you apply the Kirchhoff voltage law in the input loop by applying KVL in the input loop, you will get VCC is equals to ICRC plus IBRB plus VBE plus IE emitter current multiplied by RE emitter resistance. So if you substitute all these values, VCC is 10 volts, the collector current is given as 2.5 milliamps, collector resistance is 1 kilo ohm, base current is 25 microamperes, base resistance is not known, we need to find out that. Base to emitter voltage is given as 0.7 volt, emitter current is 2.525 milliamps, emitter resistance is 1 kilo ohm. So if you solve this entire thing, you will get the base resistance RB as 172 kilo ohms. So the answer is option A. Like the video, share the video, and subscribe to the channel for better content and more videos. For the power transistor shown in the figure, the VC saturation is 1 volt, VB saturation is 1.5 volts, beta is equals to 9. With an overdrive factor of 2.5, the required base resistance RB is. So here, the VB saturation is given, VC saturation, everything is given. Now let's apply the Kirchhoff voltage law in the output loop. By applying KVL at the output loop, we will get VCC is equals to IC RC plus VCE. So VCC is nothing but 100 volts. The collector current is not known. Collector resistance is 10 ohms. VC saturation is given as 1 volt. So from this, the collector current IC is equals to 9.9 ohms, 9 amps. So now the base current can be calculated like this. The collector saturation current divided by beta. That is nothing but 9.9 divided by 9, which is equals to 1.1 amps. But here he has given the overdrive factor of 2.5. Since overdrive factor is given, overdrive factor is given of 2.5, the actual base current, that is the actual base current that is flowing will be 2.5 times the overdrive factor times of 1.1 amps. We got IB as 1.1 amps, but the actual base current that is flowing is 2.5 times of that value. So it will be equal to 2.75 amperes. This is the actual base current. Now we got the base current. So apply the Kirchhoff voltage law at the input loop. By KVL at the input loop, we will get VI is equals to IB RB plus VBA saturation. So VI is 9 volts. The base current is 2.75 amperes. Base resistance is not known to us. We need to find out. VBA saturation is given as 1.5 volts. So with this, the base resistance RB will be 2.73 ohms. So this is the answer. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.